Hello everyone, I'm Qingwen. Today I will talk about our ECCV paper, SeFlow, a self-supervised SeFlow method in autonomous driving, the first ranked method in Argoverse 2 online leaderboard. Scene flow estimation, which determines the 3D motion field of a scene, is essential in autonomous driving. Such precise estimation at a point level enhances downstream tasks like 3D detection, segmentation, tracking, and occupancy flow. The task is to estimate a 3D flow vectors for each point in the point cloud, indicate its motions to the next time step, as shown in the red vector line here. Most of existing work focus on supervised learning, which need ground truth to train the network. According to Argover's 2 report, it's cost around $1 million to label their sensor site, where 10 times larger data are unlabeled due to expensive human annotation. Moreover, more and more data are collected, and we cannot label all of them in the world. For self-supervised existing work on optimized-based method, they can estimate flow without any training or ground truth label. However, it's expensive on time to get the results. The main reason is that the number of points in one frame in autonomous driving dataset is quite large. For example, Argoverse 2 and Waymo, where the number of points in one frame is around 18,000 to 170,000 points. And then the method like NSP and fast NSF need 5 to 30 seconds for one frame. Finally, the last limitation of existing self-supervised methods, which can run real-time, is unsatisfied performance on moving objects, especially on small size of objects. And the reason behind them is ignoring the point imbalance due to lack of the ground truth, and also ignored about the object level motion constraints. So our motivation is to train a network without human label, real-time inference for afterward autonomous driving applications, and good performance in SeFlow estimation. Here is our SeFlow architecture figures. Our network input is only raw point cloud data and go through the network backbones, then directly output the flow estimation. Well, to achieve self-supervised training, our training stage will use a dynamic awareness method to first pursue the label dynamic and static. Then we propose three novel laws on different type of constraints. The first law is chamfer distance, which is commonly used in self-supervised sim flow estimation. We add the estimate flow result to the point cloud. Then we find the nearest neighbor in PT plus 1 for every point in estimate PT plus 1. The main issue is that not all the points are the same. Like 80% point are static, so the beginning of the chamfer distance are already quite low. And the low proportion of dynamic points make chamfer distance hard to supervise the flow on dynamic points. Then we propose to use dynamic classification method to split points to dynamic and static and constrain them respectively. We use drift to classify dynamic points. It used recasting to build a void map, and then the point fall into this void region, which is the red space here, dynamic points. The example result in Argoverse 2 will look like this one. You may notice that some false positives are classified, but it's fine as it's only prior information for loss. It's lost to constrain them rather than this binary output directly. Now we have dynamic label on all points now. We replace the whole point sets with dynamic point sets as input for chamfer distance and name it as dynamic chamfer distance. Then some misalignment in the raw chamfer distance can be fixed during this dynamic chamfer distance. As shown here, the point, the nearest neighbors of this point is a static point, and the estimate flow is opposite of the correct direction. Well, if we use dynamic chamfer, then at least the direction is correct. Then for static points, we constrain that the flow of static points should be zero. Like if there are some estimate flow on the static point, then this loss will constrain all the estimates to zero. After three laws, we still have a big issue. Object level motion constraints. At the chamfer distance, it's based on the nearest neighbor. Whereas this overlapping area, all the nearest neighbor are exactly near them, I mean in the distant level. It results the zero flow estimations of middle of the object. To mitigate this effect, we propose the last loss on the object level. To get object instant information, we directly input dynamic points into HDB scan and have the cluster instant label, like all the point belongs to this cluster. Then for each point in the same cluster on T, we find the nearest dynamic point in T plus 1 here. Then we assign the upper bound flow based on the maximum nearest neighbor dynamic points we find in this cluster. And the nearest neighbor we find in PT plus 1, we don't care about the instant, so we don't use any tracking, but directly find the nearest neighbor and choose the maximum one. And we assign this is the upper bound flow of the cluster CI. Then we can have a supervised signal for the points in the overlap area to follow the upper bound flows in this cluster. Now we have all our total 4 self-supervised loss done. Here our ablation studies indicates each loss improvement compared to the first one with only chamfer distance and the last one adding all the loss we proposed. We achieved 30% decrease error. And the main table of quantitative results shows that SeFlow ranked the first place in Argoverse 2 self-supervised SimFlow estimation online leaderboard and also achieved SOTA performance on Waymo dataset. And for the training dataset, we use only 20% dataset have comparable results compared with FastFlow 3D and ZeroFlow. One is supervised learning and another one is self-supervised learning, which is 10 times a smaller dataset and less dataset, but still better result in our SeFlow method. And an interesting quality result shows our method better than the ground truth. The ground truth didn't label any floats on the shopping cart, but the real case here is pedestrians pushing a shopping cart across the road. So both of them are moving, but ground truth did only label the pedestrians flow, where our method can have a correct flow estimation on both of them. And the baseline zero flow didn't predict any floats on this small size object. And conclusion, we propose SeFlow, a novel method that integrates a dynamic classification method in formulating efficient self-supervision objectives. And we constrain the loss function to learn dynamic flow estimation in imbalanced data like dynamic and static different constraints and ensure consistent object level flows, which is the last loss item we proposed. And our SeFlow ranked first place in Algoverse 2 and achieved the SOTA performance on Waymo dataset showing that our methods are generalization. And future work is already under review now, which is a downstream task in autonomous driving. And that's all about our presentation. Scan this QR code for the code or click this link. Thank you for your watching. Stay tuned with us.